Well, I'll tell you my idea of what hypothesis testing is and what it's about, and then we'll talk about the differences between those ones with the T's and the Z's. So just be aware that you can interrupt me at any moment to ask me what I'm doing, or tell me that something I've said written doesn't match, or to tell me that I'm not writing inside the screen, or to ask me a question or to clarify something. This is your revision session, and I'm unoffendable in terms of asking me about more about what I'm saying. So just feel free to interrupt. So my understanding of hypothesis testing and inferential statistics generally is that we want to use the evidence from a sample to make a conclusion about the population, you know, or the general thing. About the population or in general. So the idea of population in statistics can be a bit vague. Most of that sounds like there's like a collection of people, for example, that you've got already, but it doesn't have to be. It could be anything at all. And it doesn't even have to exist yet. So in a quality control setting, like in a factory where you're, producing ice cream and they're supposed to have a certain amount of fat or sugar in them, then the population is like all the ice creams that could be produced by the factory. And so the population you're interested in doesn't even exist yet. And in medicine, when they use statistics, or even with people with consumer stuff, in marketing, they're like all your future consumers, and some of those people don't exist yet. And so your population is very theoretical. It's about the sort of things that might happen. So what you're going to do is you're going to compare what did happen to all the things that, to a situation that you think, to all the things that could have happened based on an assumption, and use that to decide if your assumption is correct. And so that's the idea of hypothesis testing. So you go, assume this hypothesis all that could happen, and compare to what did, and decide if what did happen is unusual compared to all the things that could happen. Did happen. Is what did happen unusual compared to what could have? That's the idea. So this is the way you choose the null hypothesis. This is where you think about the sampling distribution and the distribution of the test statistic. And this is where you either think about critical values or calculate p-values. And so null hypothesis, test statistic, and this is like critical value or p-value. Did your lecturer talk about p-values?
Yeah, he did.
Yep. Some lecturers don't. Did he talk about critical values?
Yeah.
Okay, cool. Everyone does it slightly differently, so I just want to check. And you've had a new lecturer for this. This course has had a new lecturer every semester for a while, and so things keep changing. Okay, so this is the idea, and all the things that could happen is a probability thing. You have to think of. So the classic is where you've, my ice cream thing, and you collect 20 of them off the production line, and you measure the amount of fat that they've got in them, and they've all got, 20 grams of fat per 100 or something. And not all, but there's like an average, right? Maybe you got an average of 20 grams per of fat, and you have your packaging says that it's supposed to be, 15, and so you think, well, if it was 15, what are all the things that could have happened for that one sample mean? And I compare the sample mean I've got to all those things that could have happened, and I go, is it unusual compared to those? And if it is unusual compared to those, then you go, actually, I don't believe my hypothesis. And if it's not unusual, you go, hypothesis could be true. And that's called rejecting or not rejecting the null hypothesis. And that's the idea of hypothesis testing. And the thing is that you could, if you were very, very, very clever and knew a lot about probability distributions, you could take any measurement you wanted from a sample and figure out the distribution of all the things that could happen. But that's really hard. And sometimes you don't have enough information. And so you calculate this special test statistic that makes it possible for you to have a better idea of all the things that could have happened. So yeah, that's the idea. And I'm pretty sure that in this course you've seen Z's and T's, and that's the only kinds of test statistics you've seen. Is that correct?
Yep.
Yep, cool. So I'm pretty sure that in the second year econometrics courses in the economics degree, you'll learn other ones. Did you do a chi-squared in this course? Does that sound familiar? No. Okay, cool. Just checking. Okay. I am going to just have a quick look in the lecture slides to see if I can find something. Yep. Yep. Right tails. I'm just seeing if there is a proportion test as well. Oh, this is useful. Does anyone have access to those statistical tables at all? Like in PDF form?
Yeah, I do.
Cool. If you could tell me where that is, that would be useful because I want to give it a go. Okay.
Do you have access to the My Uni page, do you?
Nah.
Ah.
I thought I did, but I apparently don't. Okay, cool. Yeah, thank you for bearing with me. This is much harder than in person. So as far as I can tell,
There's the link.
Okay, cool, thank you.
And I'll just get the other one.
That's the link to your computer.
Oh, actual?
Yeah, it says C drive.
Okay. I don't know how to do that then.
No, that's all right. Okay, so now I've got T's. Beautiful. Okay. All right, so you don't seem to have done hypothesis tests with proportions. With p-hats and that sort of thing. All right, well, that's actually very, very much easier overall than other courses which have like 15 different hypothesis tests in them. Okay, cool. I'm feeling confident that I know what's going on now. Okay. So you've been given situations where you've got all of your situations have a number that's been recorded on each individual object in your study. So every person, there might be people or there might be, they might be, what else have you got? You know, objects that are produced from a production line, that are coming off a production line in a factory, or cars. This is going to be a very bad car. Or whatever object it is, they've always produced a numerical answer. And your questions have been about those numbers. And sometimes you've had situations where not only are they a numerical answer, but there's also a group that they're in. Like they're either the old version of the factory or the new version of the factory, or it's like people who have a university degree, or people who don't have a university degree, or whatever, or, you know, two different brands of car. So they're the sort of situations that you've had where you've had to deal with hypothesis tests, as far as I can tell from scanning through your lecture notes. Okay, I think that's right. Does that feel right to you based on what having been in the course? Because that's what I'm pretty sure of. So the idea is that what you do is you take a sample of individual people or objects, and you write down the number for everybody. Everybody's got a number of their own. And then you take all those numbers and you produce a sample mean, which is traditionally called X bar. And what you're imagining is that this group of people has been taken from an even larger population of all the people that could have been, and this sample mean is somehow representative of a population mean. And so you often, the only reason you would take this information from this sample is to find out more about the population, because you don't really care what the sample mean is today. You don't care that the average comes out to 5.8 today. You're trying to figure out what the population mean is. And so the thing that you imagine is that all of the possible samples that could have been taken and all of the possible sample means that could have happened based on each idea of what the population mean could be, all of those you compare your sample mean to all the things that could have been. So you go, these the X bar, this is my X bar, and these are all of the X bars that could have happened. So you go like, assume that mu is whatever it is, and then these are all X bars that could have been. And you compare yours to that. So if yours ends up over here, you're going, oh, it's pretty unlikely. It's pretty far from the middle. That's pretty unlikely. Or if it's right in the center, you go, yeah, that's pretty reasonable. And different choices of what that mu would be would make your one that you've observed feel more or less unusual. And so the ones where it feels not unusual, they're the ones that you believe. And the p-value is the probability of getting an X bar further out to the edge than yours. But that's a little too difficult because you don't actually know quite a few things about this. So instead of doing it with the X bar and with the X bar, what you actually do is, instead of calculating the sample mean, of just calculating the sample mean, where you've got your people and they've each got a number, you get the sample mean, sure, but you actually calculate a test statistic. And the test statistic, maybe it's a T or a Z or whatever it is, the test statistic, you think, well, this is my test statistic, and these are all the test statistics that could have been, and you compare yours to all the test statistics that could have been under your assumption that the population mean is whatever it is. And that's the idea. And the reason that there are different test statistics in different situations is because how likely it is for various things to come up various things to come up, changes depending on your situation, and you know more or less about the probability. So you have to know what all of these things are. And this shape here is the distribution of the test statistic. Okay, so it seems to me that you have got, just calculate this, that you have about 8 different situations that you have to distinguish between, and it would be useful to distinguish between all of them. So each of them must have information that allows you to tell them apart. Okay. Right. All right. So the question I was specifically asked earlier was, how do you tell when to use Z or T? And that's a question about how to tell apart these hypothesis testing situations. And so that has to do with they're all numerical data, but it has to do with whether there's groupings involved, and whether there is, and whether you know the standard deviation or not. Okay, because whether there's groupings involved means the calculation you're doing is different, and so the standard deviations are different. So it all comes down to the standard deviations, and those standard deviations are what describes the probabilities of the things that you're trying to know, what, all the things that could have been, because that's about probability. So it seems to me that we have a situation where every object has a number recorded on it. And then when we think about all of the numbers that could have been, we know the standard deviation. Like that. And then we're asking the question of, is the mean equal to a particular number? Okay. Okay. Or greater than or less than or whatever it is. And then there'd be the situation where everybody has a number recorded, and you are asking the question of, is the mean equal to a particular number? And the SD is unknown. So this is the one that's most common in actual real life use of statistics, because almost never do you actually know the real standard deviation. Okay, and then you have situations where actually everybody has a number, and also we have written down what group they're in. And in that case, you're interested in, for the 2 different groups, whether mu1 is equal to mu2 or not. Okay. All right. So I think that's pretty much it. Then there will be differences depending on whether you're trying to make a conclusion about whether it's more or less than it as well. Yeah. So I just heard someone arrive. So there's going to be different conclusions as well, and so that's going to narrow this down. But these are, for me, the main ideas of what's going on in your course. And this would require you to use a Z, which would be the X bar minus the mean in the null hypothesis divided by sigma en root n. This one would require you to use a T. And this one would require you to use a T as well. I'm not sure what goes in this spot at the moment. I'd have to look that up in the notes. Okay, so it's almost never a Z. It's almost always a T. So in terms of whether to use a Z or a T, it's this. There is another situation when you use a Z, and that's when you're trying to estimate a proportion. So instead of a number, it's like a yes or no question, and you're counting in your group how many people have a certain, what percentage, what proportion have a certain result. And so this time you're interested in, based on the proportion, you know, how common is the yes or the no? And so that's the P for proportion. And so in that case, when you're trying to estimate P with P hat, that's a Z as well. Yeah, that's a whole different story. Okay, cool. Now I want you to lead me. Tell me what you want me to do. Like, are there any specific questions that you've been, you were, you know, where you had trouble figuring this out that you want me to have a go at and try and figure out? Or just ask me about what I've just said? I'm just checking to see if anyone's emailed me any requests. All right, because I really need your guidance about what you want me to talk about. Here we go. I've just had one of you send me a message. So unfortunately, I can't just go over things because I don't. I've you know, wasn't in the course. I'm not part of the teaching of this course, so I really need some guidance of exactly what sorts of things are involved there. It's really useful to have like problems that you're trying to figure out to help you in these situations. Yeah, that'd be really useful. Yeah. So for the other people who have been here already, do you have anything that you want me to talk about, or to go into more detail about this here? Feel free to use the chat window. Oh, let me have a look at that thing that you just sent. Just let me. This question here is the one that you sent. I don't know your name. I'm sorry. I've got a username, but not a name. Doug. All right. Thanks, Doug. Okay. What is the sampling distribution of a difference between the means x1 bar and x2 bar of two normal populations using two independent samples when the population variances are unknown and unequal? Okay. Right. Okay, so there's more details using two independent samples when the population variances are known. Oh, wow. Oh, cool. Okay, so it looks to me like we have some more situations that we need to distinguish between. So based on just that question, we have population variances known or unknown. Okay, and we can have the population variances equal or unequal. All right, and the samples can be independent or not. So those are the things that we're going to need to be able to distinguish between. And somehow the various combinations of these things, so I presume that there's ones where they're not independent samples. So somehow the various combinations of known versus unknown and equal and unequal and independent are going to need to be all going to have different formulas to go with them. So that's what that says to me, that question. And so I'd need to go looking in the notes to find that out. So let me have a look at the notes. So one of the students very helpfully shared these notes with me. But unfortunately, they're not very easy to read. Whoa, whoa. Oh, okay. So this one is population variance is known. All right. I'm just going to write that down. X2. All right, so it says mu1 minus mu2, but normally your hypothesis is, are they different at all? So normally that position here, just there, is normally 0. So that's all right. Because we want to know, are they the same? And if they were the same, it would be 0. N1 sigma 2 squared over N2. So let me just read this. X1 bar would be the sample mean from the first group. X2 bar would be the sample mean from the second group. Mu1 will be the population mean from the first population. Mu2 is the population mean from the second population. This would be the standard deviation from the first group, first population. This would be the size of the sample for the first sample, and then the same for the second. Okay, well, let's see what else we can find. Populations are approximately normal. Okay, so this is saying it's Z, which is from the normal 0, 1, the standard normal. All right. So I'm actually just trying to look for the differences between these things. When are there different situations? Problem object. So we have 2 unknown population variances are equal, and then 2 unknown population and variances are not equal. Okay. Right. So looks like the known doesn't have a version that goes with equal or unequal. Okay, so we just have a known and doesn't really matter whether they're equal or unequal. And then we have a second one where they're unknown but equal. Okay, and in that situation, first we figure out SP, which is N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared over N1 plus N2 minus 2. Okay, sure. And then we figure out the t statistic. Okay, and that's because we don't know the real standard deviations. Right. So the top of it is the same as it was before. We still have the x1 bar minus x2 bar minus the mu1, but the bottom is now different. Let's just compare those. I'm just going to share my computer, share my camera. So this one, when the population variance was known, it was a Z. And when the population variance was unknown, it was a T. So that's the difference. Known goes with a Z and unknown goes with a T. And then the top of the fractions are the same. They both have the x1 bar minus x2 bar and the mu1 minus mu2. But then the bottoms are different. They both have the square root, that's the same. They both have a dividing by n1 and a dividing by n2, but this one, they're sort of 1 over n1 and 1 over n2 separately. So I guess this sigma 1 squared would be over n1 is the same as sigma 1 squared times 1 over n1, and this is sigma 2 squared times 1 over n2. So if these two were both equal to SP, then this would be the same as that. So it seems to me like it's almost exactly the same, but with this and this being SP. Okay, and then this T comes from a T distribution with N1 plus N2 minus 2 degrees of freedom. Okay, now feel free to stop me at any time. This is for you, not for me. Okay. So that's useful to know, to compare the two of them to see how they're similar and how they're different. They're almost exactly the same, except for these two have been replaced with this pooled standard deviation. Rightio. Let me have a look at the next bit in these lecture slides. Okay, so we said there was a third option somewhere. Okay, so with the third option, this time we have the population variance is unknown and not equal. I'm going to copy that down. x1 bar minus x2 bar, mu1 minus mu2, the square root of s1 squared plus s2 squared over n1 and over n2. Okay, and then the degrees of freedom is, wow, that's a wicked formula. That is complicated. I don't know if you're going to have to use that formula or not. S1 squared on N1 plus S2 squared on N2 squared divided by S1 on N1. Okay, right, well, let's compare those this time. So now there's 3. So this was population variance known. Okay, so this one is almost identical to that one, but this one uses the known population variances and this one uses the unknown sample variances. Okay, so these are identical to each other. These two are the same, except that if these S1 and S2 are both equal to SP, then they would be the same. Okay, this degrees of freedom is N1 plus N2 minus 2. And this one is complicated formula. That is a seriously complicated formula. Wow, yeah. I don't know if you're supposed to remember or even use this formula. Yeah. So that's two of them. Doug, are you telling me there's yet another one that exists? Yeah, oh, you're looking at the picture. Yeah. Yeah, no, I was just trying to figure out the exact formulas for these based on what was in the notes. But you're right, Doug. Oh, and I didn't even see the second question yet. Thank you. Well, let's give this one a go so that we can see if I've got my formulas all correct. I think it's this one. No, that's the first one. That's the first one again. What am I doing? Here we go. So that's the second question you sent, Doug, by the look of it. Two independent samples of sample sizes n1 equals 8 and n2 equals 5 were drawn from normally distributed populations with mean mu and population standard deviation sigma squared given below. What is the probability that the sample mean for the first sample exceeds the sample mean of the second sample by at least 50? Okay, this question's really quite different. This isn't a hypothesis test at all. This is a raw question about what could happen in this situation. I'm just going to write down this information so that I can still see it when I'm 24,000, of course it is. Mu2 is 2357. N1 is sigma 1 squared is 88. Sigma 2 squared is 65. Okay. The mean of the first sample exceeds the sample mean of the second by at least 50. First sample mean exceeds second sample mean by at least 50. Okay. Cool. I've written it all down and now I'll try and figure it out. Okay. So I'm just going to imagine the situation that's going on here. So the situation that's going on here is that there's one normal distribution for the x1s, and there's another normal distribution for the x2s, and this has a mean of 24,000, and this one has a mean of 23,057. So not 24,000, 2,400, 2,357. And the standard deviation, the sigma 1 squared is 88, and sigma 2 squared is 65. And then we take a sample of like 8 of these ones, and we figure out an X bar, and it comes out to whatever it comes out to. And then we take a sample of 5 of these ones, and we figure out an X2 bar, and it comes out to whatever it comes out to. And then there's all these different options for what the x1 and the x2 bar could come out to. So this would be x1 bar would come out to some sort of normal distribution that would have a smaller variance than it used to be. So x1 bar should be distributed normally with the mean of x1 bar still being 2400, but the sigma 1 squared of the standard deviation of x1 bar should be the old one but smaller. So 88 divided by 8, so 11. So that's the idea here, that we need to figure out the probabilities of everything that could possibly happen. So we need to think of all the possible x1 bars that could possibly happen. And when we think about all of them, this is their distribution. They have the same sample mean, population mean as before, but a smaller variance. And so this one, the x2 bar, well, this one should be the same but narrower again. So x2 bar should be distributed normally. The mean of x2 bar should be the same as the one for x2 bar, for x2 without the bar, and the standard deviation should be, the variance should be the old variance divided by the number of things, and so that's going to come out to 13. Okay, cool. And so the thing is, these are all the options for what x1 could be. These are all the options for what x2 could be. But what we need to figure out, so we want to say, what's the probability that the first sample mean exceeds the second sample mean by at least 50? That's how I would write that. So it's at least 50 bigger than the other sample mean, x1 bar. That's what we want the probability of. Okay, well that, I don't know how to do that, because at the moment these are just all the x1s and these are all the x2s, but it hasn't got information about which x1s go with which x2s. And so I really need a brand new distribution that involves somehow the x1 and the x2 together. So I reckon if I rearrange this and I have x1 bar minus x2 bar, I can subtract x2 bar from both of those. And then this is saying that the difference between x1 and x2 bar is more than 50. And this is a new random variable. So x1 bar minus x2 bar, these two combine together to produce a new random variable, and it should be normal as well. So it's distributed as a normal distribution, and the mean of x1 bar minus x2 bar should be the same as the difference between the other two means, which would be 2400 minus 2357. So 43 is what I get. And the variance of x1 bar minus x2 bar should be what you get when you add the two variances. So because the difference between them, you could have a big one, a small one of this and a big one of this. And so you end up with more variance overall for the difference between them. And so this should be the sum of the other two variances. (24). That's what I get. That right? 65 divided by 5 is 13, isn't it? Because the 60 divided by 5 would be 12. Yeah. Okay. So that's that normal. And so when we're asking ourselves, what's the probability that this new, can I just give this a name? Can I call it D? Because then we want the probability that the difference is greater than 50. So now we have a new normal distribution. These are all the things that D could be. And it's got 43 in the middle, and its variance is 24. Okay, so this is now a question about this normal distribution. Hey there. Okay, cool. Thank you for letting me know that the answer's there. Okay, now this is all the reasoning that this stuff over here is based on. So when you do this population variance known thing, that's this calculation I was doing here. Like this is the standard deviation. So that is the variance of x1 bar, and that's the variance of x2 bar. So this calculation here is all based on this reasoning. Okay, so this is a normal distribution, and so I'm interested in this probability here of being greater than 50. So if I had access to Microsoft Excel, I could directly ask it this probability, but I don't know if you've been taught how to do that in this course. I need to check something with you. Has your lecturer, oh, maybe it's in his answer. Just a second. My question is, does your lecturer get you to use tables when your lecturer does this? Or are you allowed to use a machine to give you the answer directly? Okay, I think it's tables. Okay. So this is a normal distribution now. And so I think that since we only have a table for a Z distribution, I need to convert to Z. So I need to take off the mean and divide by the standard deviation. Like that. And then when you take off the mean and divide by the standard deviation, that becomes a Z. And whatever this number is what we need. So apparently, according to the solutions that you just sent, apparently why can I not see that? Apparently that answer works out to be 1.43. And so now we've converted this whole thing into a Z instead. And we want this probability. The Z table doesn't give me probabilities above, it only gives me probabilities below. So I don't actually have access to a Z table like the one in your course, I'm sorry, but I can look one up online. Let me have a look. Ugh. Nope. Wow, that's harder than I thought. Okay. Stop sharing this. Share this one instead. This is a Z table online. I couldn't use the one from your My Uni course, but Z tables normally only give you the left-hand side. And so I need the 1.43. There's 1.4 there. There's 1.4 there. Just a second, my computer's doing something weird. Right. There's 1.4 there, and then a 1.43 would be there. And so together, they give me this probability here. Okay, and so that's the probability of being less than, because this table only gives me the left-hand side. So when I go back to my paper, this bit here, according to the table, was 0.9236, and the whole thing is 1. So this must be 1 minus that. 1 minus the probability that Z is less than 1.43, which in my table, according to the table, was 0.9236. And so therefore that's whatever that works out to be, 1 minus that. For I think that works. If we add this on, we get, no, 7. And that's the probability. So I wrote it a little bit differently to your lecturer. I found it a little easier to conceptualize what was happening by thinking about each distribution separately. But your lecturer jumped straight to this and called it, straight to here and called it Z. So in your lecturer's solution, they went, Z is x1 bar minus x2 bar minus the difference between them that we're looking for over the square root of sigma 1 squared on n1 plus sigma 2 squared on n2, and calculated all that in one go, and then asked for the probability that Z was greater than 0, I guess. No, that doesn't make sense. Just give me a second. It's gonna look at the solution. Oh, no. This is the real mu1 minus mu2. And they conceptualize this as the 50. Well, that's confusing. Okay, so he went straight to there and went, look, if we did do this in a hypothesis test situation, we'd be asking for x1 minus x2 being greater than 50, which means we want the Z score for that is the 1.43. Okay. Yeah. So they've got this part here is the calculating of the mu1 minus mu2, like the mean of this distribution of Z, and this is the standard deviation of this distribution of Z, of x1 and x2. And so we calculate that x1 minus x2 being greater than 50 is the same as Z being greater than 50 minus this divided by that. So that's that final step that I did with the D, but I just did it differently. Okay, I got the same answer in the end though, so I presume that the lecturer would be happy with that, and if your exam's online, then it's probably entering numbers anyway. What I'd like you to do is ask me a question about what just happened there. So when you say multiple choice, the exam being multiple choice with calculations and some true or false, like how's your exam running? Like, are you supposed to be writing it and then handing it in like an assignment, like scanning it and sending it? Okay. So you supposed to be typing some things in text boxes to talk about your calculations? No? All right. Well, that's good because that would be horrible. That would be really awful. Um, hmm. Okay. So in this course in the past, you've had on already, like in past years, there's been true or false / multiple choice quizzes that you've had to do along the way. Have you had to do that this semester, like during the whole semester? Okay. Well, Doug says yes. So I presume that they're not going to be too different. Oh. So there's been no calculations to do as part of those quizzes. They've all been like conceptual things. Rightio. So I have a feeling your exam's going to be of a similar style to those things then. So is it the sort of thing where they'd give you this question that you've done, and then they'd give you like 4 options for what the number could work out to be, and you have to pick the right one? Right. And so they might have put the, we got the answer as 0.0764, but they might have also put the 0.9236 as one of the other options, which was us figuring out the wrong side of the normal distribution or something. Okay, cool. So basically you have to get it right, because guessing, there's no way of knowing unless you figure it out. Sounds stressful. So essentially it's the same as doing a paper exam, like in terms of having to figure it out anyway. Interesting. Yeah. Well, my email is the one from the, so Doug, just for the rest of you, Doug's asking me my email. My email is the same, like you can send it to the Maths Learning Centre, the one that I gave you the link from. So if you just reply to that email, then you'll get me. So what we did here is the sort of thing that would happen if you came to the Maths Learning Centre virtual drop-in centre. So we have a special My Uni course that you can get to from the Maths Learning Centre website. And if you go in there and put a post on the discussion board, then one of the tutors will come and they'll ask you some clarifying questions, and then they'll start an impromptu Zoom meeting. And this is the sort of thing that would happen in that Zoom meeting. So we'd talk to you about what your problems are and try and look up your solutions, your lecture notes with you, but we'd need to use your lecture notes, and you might give us a problem and we'll try and work through it, or have a look at the solutions you've got and try and make sense of what that solution means to you, and whether you can see the different parts of what's happening. That's what would happen if you visited the Maths Learning Centre virtual drop-in centre. The reason I tell you that is that we're open 10 a.m. to 4 p.m. Monday to Friday, all the way to the end of the exam period. So if you want more of this sort of thing, you can just jump in there anytime and the people will talk to you. But just remember, just like me, they don't have access to your MyUni. So you need to be prepared with stuff that you can share like this. I mean, you can even share your own screen rather than putting it as a picture in the chat. Yeah. It works best over there on the discussion board to have a specific question that you want to work through. So something like what Doug did and putting a picture up and saying, hey, can we talk about this, would work really well. And one of the students, you know, shared with me the lecture slides, and so I was able to look at what was there to see what happened. Yeah, so I put a link to the Maths Learning Centre website in the email I sent earlier. And on the front page, there's a big red button that says go to the virtual discussion board. In a normal semester, you could walk to it and come to the one in person, but we can't do that with coronavirus at the moment. Yeah, so semester 2, the plan is to open in person. We'll still have the virtual one for a couple of things. We haven't yet decided on that, but we will definitely have the in-person drop-in centre open as well. The university is working on how that's going to work, and we might not be able to have as many people in the centre at the same time as we normally do. But we, you know, have lots of hand sanitizer and stuff. So yes, we are opening face-to-face in person in semester 2. And the Maths Learning Centre, the in-person Maths Learning Centre, is on level 3 of Hub Central. So if you're standing in front of the Ask Adelaide desk, it's to your left. It's on the eastern side of level 3 of Hub Central, and the Writing Centre is in the same place. So there's that area has the Writing Centre and the Maths Learning Centre. I'm going to finish this up now. I don't know if the recording will be very useful, but I will put it up anyway, and at least has information about the drop-in centre in it. So thank you for coming, everybody, and for helping me to help you. Do drop into the drop-in centre between now and your exam, and you can, the virtual one, and you can get assistance with anything you're working on. It works best if you bring something specific rather than something vague. And I'll email you all on Monday when the video is ready. Thank you.